Hi everybody. My name is Bian, and I mainly work in the field of designing homomorphic encryption algorithms over homomorphic encryption schemes. And today I have this big topic of homomorphic logic gates integrated circuit design. It's gonna the contents is doesn't really live up to the title, but basically what I wish to share is some of our works in the field of designing logic gates and circuits in using I would say these kind of new homomorphic algorithm techniques. And okay, now I'll just get started with my slides. So basically, we're going to talk about two main works that we did. And one is to design a homomorphic processor, which is kind of bizarre, but the main motivation is somewhat different from, some of the mainstream application designs. What we were thinking about is that we do have this type of FHE capability where we can do gates. We can do a lot of things over ciphertext. We can do additions, multiplications. In particular, for the TFHE scheme, we can do Boolean gates over the ciphertext. And and I should have introduced myself for my background. I mainly worked in the field of integrated circuit design when I was a master's student. And that was the time when I was introduced to the concept of FHE. So I was solely working on hardware things like, transistors, voltages, currents, all of those stuffs, and didn't know anything about, a lot of mathematics under FHE. But then somebody tells a guy who works in the field of semiconductors, you can do, gates over something very different from what we're having now. So we kind of get excited. And then that's why we're kind of exploring this project. What we're trying to do is that we know that FHE can do NAND gates, and when we have NAND gates, we have functional completeness. We can evaluate the capability of Turing machines. But then problem is how can we really kind of do that? And basically we can use homomorphication to protect data, but then for most existing works back then, the algorithms of what we're doing on the ciphertext are kind of public. We can do computations over ciphertext, but what we're doing is known to the server. The server has to do computation that he or she understand. So that's kind of what we were facing. And the thing is, if we can do Turing machine, and one of the main thoughts came to us is, can we explore, how integrated circuits was designed in the field of semiconductors and use those kind of insights, move them into the field of FHE and do something different. And that was what we're trying to think about. So using fully homomorphic encryption, what we can do is to encrypt everything and let others do the work and send the result for us. But then we're not only caring about our data, we're also thinking about how can we also protect what we are actually computing, the program as well. And that's kind of, that's the backward of the motivation. We're first trying to do a processor and then trying to find what a processor different from, the usual FHE algorithm design. And what we have discovered is that if you run Boolean gates over ciphertext, and if you run something like a processor, you actually do not know what is being executed, because what the server can always see is that the server is executing a processor over and over again. But then what is happening inside that processor is actually part of the data belonging to that processor, and data are protected or encrypted under FHE. So that's kind of the whole story behind our processor design and gate design. And so today, before getting into what we're talking about, just a little bit of background. I think everybody, maybe not everybody, is familiar with. Back then, we were encountering this concept of TFHE, full encryption, homomorphic encryption over Taurus. And it was the extreme case of reducing everything down to single bit logic functions over ciphertext instead of doing large modulus RS variants and then evaluate high degree polynomials. So the bootstrapping was extremely fast, and we can do a lot of gates. So for a semiconductor guy, your natural thought comes into design automation. Basically, when we have a lot of different application and we have a subset of basic, gates, how can we map complex things down to simple gates? And that's a big area of semiconductor is about. So we kind of start to what we decided is to use TFHE to do this, is because it has a very good model, a very easy way to go to start with using for semiconductor or for logic synthesis, basically mapping applications to circuits. So maybe a little bit background on the gate evaluation. So every time when I talk to my student, because I have this semiconductor background, I always say that, in the real world, the nature do everything for you. It's the electricity that flow into the materials and the NAND computation is carried out. But then when you are trying to move everything up to this FHE thing, it's no longer electricity. You have to do the work on yourself. And this work is very heavy, which is basically the fourth step showing here. We have to first, combine the ciphertext and do the kind of blind rotate the bootstrapping procedure, and to extract the data that we need and, switch the key. So what we're trying to say is that computing or carry out gate over FHE is much, much heavier than computing gates over semiconductor devices, because on semiconductors, the electricity just flow and everything is done. On FHE, you have to actually have a processor to compute everything, and that's only corresponding to one gate. And that's actually introducing a lot of interesting things that was never seen before, because when you're using electricity, everything just flow. It's massive parallel. Electricity don't have serial. It's not thinking about anything. It's just go everything everywhere it can go. But on processors, you have to start to schedule gates because there's nothing natural here. You have to decide which gate have to execute before the other, and that's basically scheduling all of these complex computations. And in the main part, the blind rotate is the heaviest computation, and we will discuss a little bit later on how can we improve the efficiency of computing evaluating gates. But anyway, basically, our talk today is going to be divided into two parts. The first part is we're going to introduce our processor. And as we said, our goal is to achieve program hiding and data hiding with a relatively okay efficiency and using existing tool chains. And then after we have completed this processor work, it was published in USENIX Security 2021, I think. And then I think there's a lot of things to desire for designing processors over FHE, because our design was really a trivial and simple adaptation of existing processor architectures. And there are many more things that we can explore. One of the immediate thing that we have explored is the second part of this talk, which is the, let me just try. Yeah, which is the gate design and circuit synthesis. Basically, when you have a concrete target circuit to execute, you can think about how can you design better gates, and how can you better transform that circuit into a new form or a transform form such that the circuit overall runs faster. So that's basically the two parts that we're gonna discuss. I'm first gonna talk about the processor part. It's called VSP, Virtual Secure Platform. And what we're trying to say is that it's not a real processor. It's not a processor of any physical meaning. It's a virtual processor running over TFHE. Although it is a RISC-V like CPU, it's not physical. And the main feature, as I said, is that by designing a processor, we can protect the privacy of both the program and the data. And what we have mainly tried to do was to design a whole compilation and execution pipeline such that this thing can actually start to run. Okay, let me just first introduce the high-level protocol of this thing. Basically, what we do is we'll write in C program, and I think that's actually very fun. It's also a fun way, fun direction to explore in FHE. How can you let people who have no experience in FHE algorithm design to write FHE programs and to execute them? And actually, we are trying to explore in that as well. But in this framework, what we did is we let people write C program, and then we use a compiler, a general typical LLVM compiler to compile C program into instruction set architectures, basically CPU instructions, assemblies, right? And these instructions are going to be, if you go through the assembly and synthesis process, you can transfer a assembly language into machine codes, and it's going to be zeros and ones. And these zeros and ones are actually instructions to direct how the processor should go. But in both typical traditional computer and processor over FHE, these instructions are actually data. They are not a way of doing something. It's actually pure 0 and 1 data. So you have a representation of a behavior as data, and you can encrypt it. You can encrypt your program, those 0 and 1s using TFHE, and you will also send the bootstrapping keys to the server or the cloud. And what the cloud has before execution is, first, it has a topology of your processor. So it knows which gate to execute first and which gate to execute next. And then it has a big image, memory image. And in the memory image, it stores the program, and it also stores the intermediate data. We'll have a little bit more discussion on that later. And it has all the keys it needs to evaluate ciphertext over FHE. So then what it does is what I have kind of discussed. It has to start to execute each of the gate, and these executions do not happen in parallel. Each gate will take up all the computation power of a standalone processor. So in the experiment, we did a lot of experiments using parallelized hardware architectures, but basically you cannot just simply parallelize a lot of FHE gates and try to increase the speed. So you have to have something called an evaluation engine, such that different FHE gates can be scheduled in the correct timing to your hardware resources. And basically, what this evaluation run is the processor, and when the processor run, you can think of it as a Turing machine, right? The head kind of read a line on the tape, and then depending on what the line says, it will jump to another place on the tape and write something maybe. So after this repeated execution of the processor, you get a resulting tape, right? You get an output image of your memory. And inside that memory, it stores maybe a lot of garbages, but also it stores the output or the result of the program execution. And then we will send that whole memory image back to the client such that the client can decrypt the output image and see what has been calculated based on the program. And basically, what we are the cost of the client is to encrypt the memories, and it does not have to do any computation. And what a question that we have got is, is the work of the client strictly less than if the client just do everything locally, right? And actually, that's a very interesting problem. And for us, it's that it comes down to the problem if P space is harder than P time, right? Basically, when you encrypt the whole memory, you are encrypting your work is corresponding to the size of the storage space of a program. And what you have outsourced is the computation of the program. And as long as computing is easier than storing, this thing goes. And what we kind of explored that a little bit, and what we have come down to say is we do think that P space is harder than P time. So this thing is meaningful. Anyway, so that's basically the entire protocol flow. And just some small points is that first, processor architecture we're going to show a little bit later is a simple pipeline processor. And I think we were kind of the first to explore how to design pipeline processor, or what really does a pipeline mean on FHE. And because we have adapted a existing RISC-V ISA or instruction set architecture, we can use existing compiler, both front end and back end. We can directly compile any program into our ISA and just run it on our processor. And the thing that we have also talked about is that it is a virtual design. It's a logic thing. It's not a physical thing. And we use Chisel to design the overall processor. And the gates, we kind of use the given gates in the TFHE, like first earlier version of TFHE library, where we have AND NANDs, or a little bit 2 input, 3 input ANDs, and except we have redesigned the memory, because the memory is a very strange unit for FHE to handle. And then the thing that I kind of wish to say is that flip-flops or storing things on FHE does not require logic gates. It requires logic gates physically because you cannot just store electricity. But because FHE ciphertexts are just data, it can be stored on memory. So you do not have to design an extra unit to keep it. So there's no wires, no clock tree, no timing violations. It is a very different design scheme or dev paradigm. And so it was really interesting to do something like this. And again, we have kind of designed different backends to accelerate the overall processor evaluation. So here's kind of a very rough overview on the processor. And I'm not sure how many audience here is really familiar with computer organization, because this is basically a hardware kind of class. And we're just gonna briefly summarize. We have designed a 5-stage pipeline. So we have different pipeline stages where the intermediate data is stored to a register to pause and to allow different stages to work independently. Basically, that's what how pipelines works. And this 5-stage pipeline is textbook level unoptimized. It's basically what every undergrad student will design on their own. Is this kind of simple architecture of a processor. So we have really not do a lot of optimizations for FHE. We were just trying to see if this thing is gonna be able to go. And so basically, the one biggest thing that we want to see if pipelining is trying to go, because pipelining was a technique for traditional electrical processors. And just gonna throw out the conclusion, what we have found is that pipelining in FHE basically can increase the amount of parallelize the gate execution. So if you have a lot or infinite amount of processors, pipelining definitely is going to help. And another thing is that basically in the earlier days, very early days of computer, we have this hardware architecture and von Neumann architecture, where the decision is if you're gonna put together the memory, put the data memory and the instruction memory together or separate them. And on modern computer or electronic processors, it really doesn't matter because the semiconductors are so powerful. But on FHEs, the thing is, if you have a read-only memory, ROM is basically read-only memory. It's much easier to design a read-only memory than a read and write or random access memory, because when you have to write things, you have to change ciphertext and you have to decide where you want to change that ciphertext. So it's very hard. It's much harder to design a memory that you can both read and write than just something you can read from. So that's why we kind of adapted a hardware architecture, and we use the read-only memory to store instructions, and the read and random access memory to to store the intermediate results during program execution. And the other thing is that if you think about a memory, it's basically address decoding and data fetching, and the most amount of computation happens in the memory decoding, because you have to decode a binarily encoded data into an exact one-hot representation to select the thing you want to read or write. So instead of building up this decoder using binary Boolean gates, what we have found is that the CMUX operator proposed in the original TFHE manuscript is extremely good at handling deep tree of selectors. Basically, is almost 100 times faster than building these decoders using gates. So basically, it kind of here, what we're designing is we look at a processor architecture, and we are trying to get every detail right and fast, such that we can execute this thing and get a reasonable speed. A little bit more word on the CMUX memory. I was conservative. It's actually 1,000 times faster than just building up using gates. And one problem here is that when you're trying to use the CMUX, you have two data to be selected, and you have a selector. The selector has to be in the GSW format because of the noise problem. And to convert, but the thing is, when you're trying to execute the processor, the entire processor is basically based on the integer learning with error ciphertext. Basically, you just have A and B, where A is a vector and B is one single integer. So you have to execute this thing called circuit bootstrapping to convert the address bit to a selector, such that you can, based on the address, to select the data you want to read or write from the memory. So this is the I mean, using CMAX it becomes faster, but transforming the address bit from a LW ciphertext into GSW ciphertext is actually very expensive. So this is not a technique that we can use everywhere. And second, when you have a very deep tree of CMAX, you have to insert bootstrapping to stop the error from going too much. So I think memory is very hard to design because what we're trying to do on the other research direction is to design how to say databases over FHE. And if you think about it, databases is basically a memory. And it is actually very hard to I mean, reading from a memory or reading from searching in a database is kind of reasonable. But then if you really want to write a lot of data and to read a very long databases, it's a common problem, and it is very hard to do over FHE because the fundamental problem is we cannot see what we're computing, right? So we cannot see what these selector flags are. So that's what made this reading and writing from the memory very hard. Anyway, so before getting into this is basically the results page for our processor. And before getting into explaining the result, I'm just gonna have two kind of remarks on why this thing runs slow. It runs very slow, but why it runs slow? The first problem is, and both of these problems come from the fact that we don't see the comparison results, right? So because we cannot see comparison results, our processor execute every instruction in every cycle. So for basically any smart people will try to execute only one instruction. If you want to perform add, you just execute the add instruction. But because we don't know what kind of instruction are you trying to perform, the only thing we can do is to execute every single instruction and multiply them with the selector provided by the client, the encrypted selector provided by the client, and add things up. If I'm not executing that instruction, the execution result will be cleared to 0. If I'm executing that instruction, I'll get that instruction. And if I add everything up, and if there is only one instruction being executed, that's what we get. So because we don't know what we're executing, we have to execute every instruction in every cycle. And the second thing is we cannot reveal what kind of memory address are we reading, writing, as such. So in FHE, in an FHE processor, we write every single memory address every single cycle. So if we execute an instruction, whatever it is, add, multiply, or something, we will always write to every address of the memory to make sure that the server does not see what kind of address did we write in. So combined with the ciphertext expansion of encrypting bits, what we're getting here is basically we designed a 512 bytes ROM for storing programs and 512 bytes RAM for storing intermediate results. We are benchmarking a program of computing 8-bit, the Hamming weight between two 8-bit integers. And what we're getting is we tested on two machines. One is a 96 core CPU machine, and we're getting 2.5 seconds per cycle. And as we said, they're actually, because the gates have a lot of parallelizability. So we rerun the experiment on a 16x large AWS machine, which is basically a machine equipped with 8 V100 GPU cards, and we try to accelerate using GPU. And what we have get is we can accelerate it further to get the best time we recorded is 0.8 second, roughly 0.8 seconds per instruction, which translates to a core frequency of 1.25 hertz. If you guys have phones, our mobile phones runs on a core frequency of about 1.25 gigahertz, and the FHE processor runs only 1.5 hertz. So the difference is 10 to the ninth power. I have to say it's very slow, but what we are really able to do is to really hide what program are we executing and along with the data. So we can trade a lot of efficiency for that security. So yeah, that's basically the first part of our work. And do I have, okay, I don't have a, so basically, after doing that work, the immediate thought came to us is, how can we make this thing run faster? And one of the easiest way of making it run faster is to design better gates. Because basically we have had two works. First is this WHC work on 2021, where we kind of made our first step in designing multi-input gates, and then after that, the programmable bootstrapping came up, and we kind of start to understand what we were exploring. Basically, what we're have found is that given the LW parameters, we can do more gates than just and or and those simple fundamental gates. So what we have found in this work is that we can do a half adder. There are 2 to 3 gates in a half adder. So you can do multiple gates using one bootstrapping, and that will increase your evaluation of the circuit by 2 to 3 times, or even more. I mean, the highest was probably around 8 times, because you can just pack a lot of things into one evaluation of bootstrapping. And so what we have had is basically for a 16-bit multiplier, we can run 2 times faster, and for adder we can run around 5 times faster in that work. But I think the problem we have had is that it's kind of an empirical design. We're just trying to test and see if these gates can be run, and there was no methodology. So that was the main motivation for our second work, which was published this year on actually it's a journal in the field of circuit design. And people were getting interested on how to apply, design automation techniques into FHE circuit design. So that was basically our second work. We were trying to explore how can we understand what kind of gate can we design. And second, if we have a lot of gates, because if you are familiar with semiconductor, you don't really have a lot of standard cells, because it's very hard to manufacturing the different topologies using actual physical devices. But on FHE, we don't have physical things. It's just mathematical and adding things up. So we can actually easily generate a lot of different compound gates. And so the problem gets into, if we have a standard gate or representation of a piece of hardware, how can we automatically transform that thing into our very enriched compound gate library such that it runs the fastest? And I think trying to generate the optimal design is a NP hard or NP complete problem. But so that's why in this work we also use heuristics to complete the task. Okay, so I think we are kind of, the task a little bit longer than I thought. So I'm gonna go a little bit faster. And this all flow is our basically the entire idea, and it's actually not very hard. Basically, what we do is we have a representation of a circuit, or something we call netlist in the field of design automation. And we first transform that into a graph, circuit graph. You know, we have a lot of gates, and that's exactly what we do when we were designing the processor. You transform the processor circuit into a graph. And then the other thing that is the thing here is critical is we're trying to perform something called truth table matching and gate generation. So basically, we will start to look at regions of circuits to see if these gates can be merged together to form a compound gate. And the method is basically we'll encounter a node and just explore using, you know, graph algorithms, explore its neighborhood, and try to generate a homomorphic FHE gate that can perform the functionality of that particular region. And if yes, we'll just replace that with a multi-input and single output gates. And if not, we'll just go to the next node. And yeah, so that's basically the replacement part. And lastly, I think this actually is a recent paper, 22 or 23, I forget. What we have seen is that if you evaluate different functions, for example, if I have AND gates, OR gates, and XOR gates, all of the inputs for these gates are the same. And then we can actually use the multi-input and multi-output gates to further reduce the number of bootstrapping or TFHE bootstrapping that we have to execute over the circuit. So we'll do all this optimization and then generate a new topology netlist that have all these compound gates that we have. So basically, we transform a existing and or simple gates netlist circuit into a compound gate circuit automatically, such that the runtime can be significantly improved. Because of time, I think I'm just skip all the TFHE details. Basically, I think the key idea is very similar to programmable bootstrapping. You just try to find different combinations of the inputs, such that when you're rotating this disk, you can get the correct output if you want. And one of the interesting parts is how can you minimize the size of the lookup table. Basically, when you trying to combine a lot of inputs, your test vector tends to be much longer than you can actually handle under reasonable runtime. So a optimization problem is given a functionality, right? When you are giving a truth table, how can you arrange those values such that your test vector is the shortest? And there are a lot of interesting tricks. For example, if you have a gate whose output is completely irrelevant to its input, you don't have to do any computation. You just output the predetermined value. And if you have, for example, if you have AND gates, when you have an AND gate and when you have one of the input is 1, the other is 0, it doesn't matter which one is 1, which one is 0. The output will always be 0. So you can use that kind of topological information to optimize your test vector generation, such that you can squeeze more gates into one blind rotate evaluation. The extreme case we have had is you can evaluate a 32 inputs AND gate using just one blind rotation, because the AND gates is highly regularized, right? There is only one case you have to output 1. The other case you always output 0. So those are the interesting design tricks that we can do on FHE that we couldn't do on semiconductor devices. Yeah, so and the other thing is the multi-output. When you have this, when two gates share the same input, you can just avoid doing blind rotate again and just use this multi-output technique. These are known techniques, and we didn't invent it, but we kind of use it, adapted in the case of circuits. We did a lot of noise analysis because it's very important to minimize the parameters, and details can be found in our paper. And as the result, I think we really have had a big improvement over existing works. Compared to pristine and or simple gates, we can sometimes achieve 6 to 7 times faster on standard benchmark circuits. And we also analyzed our error to ensure that the decryption fail probability is reasonable. Yeah, so that's about the second part. Just as an overall wrap up, sorry, I'm kind of taking too much time. We focused on how to design better gates and circuits over FHE, and I think it's very interesting because designing circuits over FHE is very different from those on physical circuits. And I think there are a lot more to desire in the field. But then we'll try to explore if there are any other directions that we can work with. And really happy to share with you guys with our work, and very excited to take any questions if you have. I think that's about for my talk. Thank you.